IES Technology Electronics Tutorial. Junction Field Effect Transistor. Core concept. What is the field effect transistor? Voltage-operated device. The FET uses the voltage applied to the gate terminal to control the current flowing through its channel, making output current proportional to input voltage. Electric field control. Operation relies on an electric field generated by the input gate voltage, hence the name, field effect. No input current is required to control output. Unipolar semiconductor. Unlike bipolar transistors, the FET depends only on conduction of electrons, N-channel, or holes, P-channel, not both simultaneously. Very high input impedance. The FET's input impedance, RIN, is thousands of ohms, far greater than the BJT, making it extremely sensitive to input voltage signals. The FET's high input impedance makes it ideal for integrated circuits, preamplifier stages, and CMOS digital logic. Though this same sensitivity means it can be easily damaged by static electricity. JFET construction and terminal comparison. The JFET has no PN junctions in its main current path. Instead, a narrow piece of high-resistivity semiconductor material forms a channel of either N-type or P-type silicon, with 2 ohmic electrical connections at either end, the drain and the source. Gate applied. Voltage is placed on the gate terminal. Depletion forms. Reverse bias creates depletion regions. Channel narrows. Conducting channel width is reduced. Pinch off. Channel is pinched off at VP. The gate forms a PN junction with the main channel. A reverse-biased gate voltage widens the depletion region, squeezing the channel until pinch-off occurs at voltage VP. The JFET acts like a voltage-controlled resistor, zero resistance at VGS equals 0, maximum RDS when gate is very negative. Terminal reference. JFET versus BJT, key comparisons. Understanding the JFET is easier when mapped to the familiar bipolar junction transistor. Both are 3-terminal devices, but they differ fundamentally in how they are controlled, their input characteristics, and their channel behavior. 3 terminals. Source S, gate, G, and drain, D, corresponding to emitter, base, and collector of the BJT. 2 channel types. N-channel, electron flow, lower resistance, more efficient. And P-channel, hole flow, reversed bias polarity. Almost equals 0 gate current. When reverse biased, gate current is practically 0, unlike the BJT base which always carries some current. ID equals IS current equality. No current flows into the gate, so source current equals drain current at all operating points. 1000 omega input impedance. The JFET's input impedance is thousands of ohms, comparatively far higher than the BJT. VP pinch-off voltage. The gate source voltage at which the channel closes completely, analogous to BJT cutoff region. N-channel JFETs have greater channel conductivity than P-channel types, since electrons have higher mobility through a conductor compared to holes, making N-channel devices more efficient conductors. Operating regions. For operating regions of the JFET. Ohmic region. When VGS equals 0, the depletion layer is very small and the JFET acts like a voltage-controlled resistor with minimal channel resistance. Cutoff/pinch-off region. Gate voltage VGS is sufficient to act as an open circuit. Channel resistance is at maximum, the depletion region closes the channel entirely. Saturation/active region. The JFET becomes a good conductor controlled by VGS, while VDS has little or no effect. This is the normal amplification region. Breakdown region. VDS is high enough to break down the resistive channel, causing uncontrolled maximum current to flow, a destructive condition to avoid. In the active region, drain current ID is calculated using the Shockley equation, ID equals IDSS, 1 minus VGS/VP, superscript 2. The channel resistance RDS is given by RDS equals 1/GM, where GM is the transconductance gain representing the rate of change of drain current with gate source voltage. 3 modes of FET operation. Like the bipolar junction transistor, the field effect transistor is a 3-terminal device capable of 3 distinct circuit configurations, each with different impedance characteristics and signal phase relationships. Common source, CS. Input applied to the gate, output taken from the drain. Most widely used configuration, high input impedance, good voltage amplification, 180 degrees output phase shift. Ideal for audio amplifiers and high impedance preamp stages. Common gate, CG. Input applied to the source, output from the drain, gate grounded. Low input impedance and high output impedance. Used in high-frequency circuits and impedance matching. Output is in phase with the input. Common drain, CD. Input applied to the gate, output taken from the source, also called source follower. High input impedance, low output impedance, near unity voltage gain. Used in buffer amplifiers. Output is in phase with input. Biasing and application. The JFET common source amplifier. Just like the bipolar junction transistor, JFETs can be used to make single-stage Class A amplifier circuits. The JFET common source amplifier has characteristics very similar to the BJT common emitter circuit, with the key advantage of significantly higher input impedance. Gate biasing network. The input impedance is set by resistors R1 and R2 in a voltage divider network. Since gate current IG equals 0, the DC quiescent voltage is set solely by R1 and R2 selection. Source resistor RS. The voltage across source resistor RS is generally set to about 1/4 of VDD, VDD/4. This sets the operating point and provides self-bias stability for the amplifier stage. Solid-state switching. Control of drain current by a negative gate potential makes the JFET useful as a solid-state switch. The gate voltage must never go positive for N-channel devices, or channel current will flow into the gate, damaging the JFET. Key takeaways. JFET summary and next steps. The junction field effect transistor is a depletion mode, voltage-controlled, unipolar device offering very high input impedance and low power consumption. Mastery of JFET principles forms the foundation for understanding all modern field effect devices. Understand JFET fundamentals. The JFET is controlled by gate source voltage, VGS, not current. The depletion region widens as VGS becomes more negative, reducing channel conductivity until pinch-off at VP. Master the 4 characteristics. Study the 4 operating regions, ohmic, cutoff, saturation, and breakdown, and learn to calculate drain current using the Shockley equation and transconductance GM. Explore the MOSFET. The next evolution is the metal oxide semiconductor field effect transistor, MOSFET. Where the gate connection is completely isolated from the main current carrying channel by a thin oxide layer. IES technology. Contact us for repair service. Telephone, 711-71041, 502555686. Email, info@icetechnology.com.qa. Web, www.iestechnology.com.qa.